So we've talked about how to use the receiver to identify the location of a ground fault. Now let's talk about the current clamp. And the use case for the current clamp is a little different, but it can give you the option to get more information because we're actually measuring the signal and you can see the results directly on the screen of the current clamp. When measuring with the current clamp, you kind of want to do it in two different ways. You can use the current clamp to identify which string has the ground fault without making disconnections if you have access to be able to put both the positive and negative conductor of a single string into the clamp at one time. If you do that, strings that do not have a ground fault, the signal flowing through the positive and the negative will cancel each other out and you'll get a 0 on the clamp. The string with a ground fault, because some of the signal is going to the ground, you'll see an imbalance and it will show a reading on the current clamp. That will allow you to identify which string has the fault. Now, to get out into the array is kind of the second step of that process. And if you can measure both conductors going through the array, you can continue that process. But more likely than not, you're not going to have both the positive and negative conductor directly next to each other out into the array. And that's where making a disconnect on either the positive or negative side will allow you to use the current clamp more effectively on single conductors out in the array. In this case, I have the fuses on the positive side of the strings. So I would remove the fuses on the positive side and inject the signal onto the negative to ground. That's the position of the dial in the fault function. Once I've done that, the signal is going through the negative bus bar, down the string with the fault, and through the ground fault back to the ground. I can then take the current clamp and go out into the array and find the wire that has the signal on it and trace that until the signal stops, and that would be the location of my ground fault. In a trunk bus system, we often start with the transmitter at the DC disconnect, and that's sending the signal through the entire trunk bus system. Once we use the clamping on pairs of conductors to identify the branch circuit that has the fault, it's often easiest to then move the transmitter to that single string and then transmit that single string to find where the ground fault is located. We can also do essentially the same process in a combiner box or an inverter that has quick connectors on the bottom of the box. In the United States, it's very common to have what we see here, which is a conduit coming in and the conductors coming in through the conduit. In many other locations, it's more common to have the single conductors going into the bottom of the box with quick connectors like an MC4 type connector. We can actually inject the signal from outside the box without even opening the combiner. We can shut the disconnect off, assuming again that it disconnects both the positive and the negative side of the output circuit. And then I can actually remove one of the circuits from the bottom of the box. I would test that individual circuit first to make sure that's not the circuit with the ground fault. And then I can use the two terminals on the bottom of the box from the circuit that I just removed to inject the signal in through the bus bars of all the other circuits in the box. Then I can use the current clamp, measuring along pairs of conductors to find the individual circuit with the ground fault. From there, I could remove the transmitter from the combiner box, isolate that single string, and put the transmitter on that single string to then use the clamp out in the array using single wire measurements to identify the ground fault location.